we try to make sense of a data set. So let's assume we have a bunch of snapshots, webcam snapshots, which are characterized by two features, x1 and x2. And we want to make some sense out of it for the sake of easier processing or then more convenient representation of the data. And we heard about clustering methods. So there are two main flavors of clustering methods. What are the two main flavors of clustering we have looked at? Yes? K-means clustering is an example of a hard clustering method. So we associate each data point. So this, for example, here is one data point. Might be one feature vector, characterized by a feature vector which has two features, x1 and x2. And we try to organize it or group it into clusters. And there are two principal types of clustering algorithms. One algorithm, type of algorithm is called hard clustering, where we have a clustering such that each data point belongs to one and exactly one cluster. Okay? And K-means does that for us. Another approach, which I started to discuss in the last lecture, is soft clustering. And in soft clustering, we allow the clusters to overlap. So we have here a cluster, might be cluster 1, and another cluster overlapping cluster 2. And in soft clustering, we try to find, or we try to associate to each data point, for example this here, degrees of belonging. So what is the degree of belonging of this data point to cluster 1? We denote this by yi1. And what is the degree of belonging to cluster 2? yi2. And these degrees of belonging, for the sake of notation, we constrain to be within the interval 0 to 1. So 1 means belongs fully to one cluster, 0 means belongs not at all to a cluster. But how do we come up with a scheme or an algorithm to map each data point to two such numbers, to these soft cluster assignments? How to come up with a principled approach to map data points to soft cluster assignments? And I tried hard within this lecture to avoid any probabilistic models. So you can explain pretty much everything about machine learning validation, how to fit, how to do a linear regression without any probability theory. However, I don't know any other way to formulate soft clustering or to come up with soft clustering algorithms except then using a probabilistic model for the data. So now I cannot avoid it, I'm sorry, we now have to bring in some probability theory. And this goes as follows. We represent a cluster by a distribution. Represent, for example, cluster 1 by a probability distribution. And in particular, we represent a cluster. So what probability distributions are you aware of? Have you ever encountered something like a probability distribution in your life? A Gaussian, Poisson, yeah. So these are just modeling concepts. This is a concept like a hypothesis space, an abstract concept. You don't see Gaussian random variables in practice, you just see numbers, measurements, bits, bytes, text in practice. However, it turns out to be useful to model what you see, the data, as realizations of random variables, and random variables have some probability distribution. And here we use probability distribution models. So I have heard already one possible choice for probability distribution of a feature vector, two-dimensional feature vector, could be a Gaussian distribution. And we denote the Gaussian distribution like this, calligraphic n, then the random variable, the generic symbol for the random variable. So this here means a random variable. a random vector, in our case, two-dimensional random vector. And a Gaussian distribution has parameters. What are the parameters of a Gaussian distribution? Yes? A mean, vector, and a covariance matrix. Or let's use the symbols. It's always a difficult question which letters to use. Let's say M for mean and C for covariance matrix. So the mean of this random vector can be represented here, for example, using this dot. So this might be the mean of the first cluster, or the probability distribution which we use to represent cluster 1. And the covariance matrix, so this here has a superscript 1, because we use one distribution for each cluster, so this distribution for cluster 1. And we can also express the spread, the shape of the cluster, using the covariance matrix. So the covariance matrix of cluster 1, or of the distribution that represents cluster 1, somehow represents the shape of cluster 1. And we do the same, another probability distribution for cluster 2, the mean of cluster 2 and the covariance of cluster 2. So here we might have the mean, and here we encode the shape of cluster 2 by a covariance matrix covariance matrix C2. Okay, so that's just a model. We come up with a model that tries to explain the data that we see as realizations or draws from a probability distribution, which is a Gaussian or multivariate normal distribution of a Gaussian random vector, to be precise. Okay, so far so good. So do we know these parameters here? Typically, when you had in your assignment the task to implement a soft clustering algorithm, so did we provide you the cluster means and the cluster covariance matrices? These are parameters of this probabilistic model. How did we get these parameters? Was it thrown to you by some higher instance? You had to estimate it. You had to iteratively estimate it. Okay? But let's now assume for the time being that we know the parameters. Somebody tells you, well, for example, by looking at the data, you see that the mean, it would be good here to use a Gaussian with mean vector here, and the covariance matrix whose shape corresponds to this somewhat tilted ellipse. Let's say we have it. Let's assume, for the time being, these mean vectors and the covariance matrices given. Somebody gave it to us. We have a vector with numbers, with entries, and covariance matrices, we know it. Okay, so what can we do now further? We represent a cluster by a probability distribution. And then a particular data point, xi, so the first, for example, the first feature vector that comes along into your data set is a draw from one of these distributions, from such a Gaussian distribution with some mean vector Ci and some covariance matrix Ci. So this here, the Ci, is the cluster indicator or cluster assignment of data point xi. So this variable tells you from which cluster did we draw the ith data point. So Ci is an element of the set 1, 2, either cluster 1 or cluster 2. Do we know the cluster assignment? Do we know from which cluster this, for example, this data point has been drawn? Does somebody throw it to you? What are the cluster assignments? Well, what is the goal of clustering? To find out the cluster assignments. Exactly. So the goal of clustering is to find these cluster assignments. We don't know them. They are unknown. So these are unknown. However, we can always model anything as random variables, so we also model this as random variables. However, these are random variables which are not seen. They are somewhere exist, they are random, but we don't measure them. We don't observe the realizations of these random variables. All we observe is the realization of this random variable. So somehow we need to connect these unknown random variables, which we would like to know or like to estimate, with the observed random variables, which are the feature vectors. So how are these related? How are random variables related with each other? Well, we could ask, what is the probability that the cluster indicator takes on, for example, 1? So what is the probability that the true underlying cluster would have been 1 based on the observed feature vector? Similar, we could ask ourselves, what is the probability that the cluster assignment is 2 based on the observed feature vector? And then we get some numbers for those, which tell us what would be the probability of, on average, how likely would have been the true underlying cluster index 1 given the observed data. Does that make sense? So once you have a probabilistic model and you model every quantity as a random variable, some of the random variables you observe, like the feature vector, some of them you don't observe, like the cluster assignment, but which you're interested in, well, what you do, and in probabilistic machine learning relies on one approach, or one quantity, which is this here. You condition on all the quantities you observe and compute the posterior probability, this is called the posterior probability, of what the value of the unknown quantity, which you would like to know, is given the observed data. This is the key idea underlying any probabilistic machine learning method. And you will hear, I mean, it sounds super easy, but in practice, the difficulties are, how do you evaluating this probability density function or probability distribution is highly non-trivial and difficult. And you hear in 2 courses, at least 2 courses I'm aware of, Bayesian data analysis and in advanced probabilistic models, you hear different powerful methods to compute this conditional probability distributions. But the idea is simple. You just evaluate the probability of what would have been the value of the unknown quantity given all the known quantities. Yeah, and actually it comes up pretty naturally how we define here or what the degree of belonging could be. Well, we define the degree of belonging simply. So the degree of the data point I belonging to cluster 1 is just the posterior probability of Ci equal to 1 given the observed data point. The probability, the degree of belonging to cluster 2 is the posterior probability of cluster index being equal to 2 given the observed data point. Does that make sense? Well, by the way, naturally, this quantity is between 0 and 1, which is what we would like to have. By construction, these 2 quantities, if you sum them up together, what do you get? 1. Yeah, if you sum up all the probabilities of elementary events, which together make up all possible events, so the cluster assignment can only be 1 or 2, either one of 2, and if you sum them up, then you get 1. That's called the law of total probability. Okay, so let's define the degree of belonging like this, and how do we calculate it? Well, we need to find out what this posterior probability is. And it turns out that it's easier, or what is more natural, is to get the probability in the other direction. So the probability, the conditional probability of xi given that the cluster assignment is 1. Because this means what would be the probability distribution if this data point is drawn from cluster 1? Well, what is our modeling assumption? Cluster 1 is represented by this probability distribution. So we know it by construction of our model. So this is normal distribution with mean vector M1 and covariance vector C1. C1, yeah, sorry. So, and what is the conditional probability distribution of Ci equal to? The same thing, but the probability distribution for cluster 2, which is a multivariate normal distribution with mean M2 and covariance matrix C2. So this is pretty straightforward. This follows, basically follows from the definition of our model. And this model is called a Gaussian mixture model. This is a Gaussian mixture model. Mixture model. Okay, so how can we use these two expressions for the conditional probability of the data point given the cluster assignment to compute the conditional probability of the cluster assignment given the data point? What fundamental rule in Bayesian statistics helps you here? How to turn, this is called a priori distribution. How to get from this priori distribution to the posterior distribution. Which rule is used here, or can be used? Bayes rule, exactly. We use Bayes rule, which tells us that the probability that the cluster assignment is 1, given the observed data point xi, is the conditional probability the other way around, xi given ci equal 1 times the prior probability that ci is 1 divided by the sum of all these probabilities for I equal 1 to 2. No. Times the probability of xi. So this is Bayes' rule. Bayes' rule. This we know by construction. This is this here. What about this here? Do we know this probability? So the probability that the cluster, that the ith data point is generated from cluster 1. Do we know this probability? Do we know what is the proportion? How often does a data point come from cluster 1 and how often does it come from cluster 2? Yes? Yeah, we don't know it. We don't know it. So this is some number, some unknown number. We call it cluster probability, PC, which is, or let's say P1, which is between 0 and 1. And there's a cluster probability for the other cluster, which is between 0 and 1. They have to sum to 1, have to be within 0 and 1, or otherwise unknown. So P1 and P2 are also parameters of our model, of the Gaussian mixture model. Okay, so what do we do? Well, we assume now also that we know this, so that we know P1 and P2. Well, then we can insert here, and we can evaluate Bayes' rule to get the degrees of belonging. So this is our, as we defined, our degree of belonging, y1, yi1, and similar we get yi2. And these, as we define it, are just the posterior probabilities of cluster assignment being equal to 1 given the observed data point. Okay, so far so good, but we used a lot of knowledge that we don't have actually. We used all these parameters. So to recap, for this, we need, to compute this, we need the Gaussian mixture model parameters, which are the cluster probabilities, P1, P2, the mean vectors, M1, M2, and the cluster covariance matrices, C1, C2. Yeah, we need those. So this cluster mean vectors and covariance matrices, we need to evaluate this conditional probability function because this is the evaluation of the Gaussian distribution. And in the Gaussian distribution, so if I may write this out, what does this mean? This means 1 over square root of the determinant of 2 pi covariance matrix C1 times exp exponential function of xi minus m1 transposed covariance matrix inverse and so on and so forth. So if you should know one probability distribution by heart, my recommendation is this Gaussian distribution. This is an expression which involves the mean vector and the covariance matrix. So if we know only the realization here, xi, this we know. Here we get a vector, a number, particular number. But in order to evaluate the probability distribution, we also need to know the mean vector and the covariance matrix. And these are parameters of our Gaussian mixture models, and nobody tells you what these are given the data. You have to estimate them. So what do? Well, we start with a random guess for those. Start with a random guess, as always. And then we can evaluate these posterior probabilities or cluster assignments. And again, we turn the problem in the other direction. Using these new guesses for the cluster assignments, we compute new estimates for the cluster probabilities and for the mean vectors. Okay, this is the other update step in the soft clustering algorithm, which I'm not sure if you had to implement it or it just was a demo in the notebook. So update these parameters. And what do we do with the new parameter guesses or the updated parameter estimates? We update the degrees of belonging or the posterior probabilities. Update yi2, yi1. Okay, what do we do then after 2 updates? Should we stop? Why not? Sorry? So we have to repeat it until convergence. Yeah, and what do we mean by convergence? Well, we can check how, so in the course of the soft clustering algorithm, we produce more and more refined estimates of the parameters for the Gaussian mixture model. And this Gaussian mixture model provides us with a probability distribution of the data points. And this probability distribution, so this probability distribution looks like this. It's so if I draw it here schematically only in one dimension, this is the one data point, and this is drawn from a probability distribution, and this probability distribution is the sum of Gaussians, a mixture of Gaussians. Here we have one Gaussian with mean vector m1, here another Gaussian with mean vector m2, and we specify, Gaussian mixture model specifies a probability distribution for these feature vectors. And this probability distribution depends on the parameters, of course. C1, C2, and the cluster probabilities, P1, P2. And running the soft clustering algorithm provides us with estimates of these parameters, which we can then use to evaluate the probability that we observe precisely the data points that we observe. And if this probability is 10 to the power of minus 100, then this tells you that these estimates, these parameter estimates that you have here are crap, or you have not converged. So if this becomes somewhat near 1, or the maximum, you can work out what the potential maximum is. It's not 1 because it's a density. So if this is a reasonable number, 10 to the power of minus 1, for example, and it doesn't change anymore, so you in particular, you monitor the change of this probability or evidence values, The evidence is the probability that given the model that you use, in this case a Gaussian mixture model, you actually observe the data points that you observe. It's kind of trivial, sounds trivial, but that's what you can do to fit the model. So it's again nothing, soft clustering method is nothing but fitting a model, a Gaussian mixture model in this case, which is a probabilistic model, which depends on parameters like the mean vectors and the covariance matrices, and you try to fit the model by tuning these parameters in order to make the probability that you observe the data that you observe is high. Pretty intuitive, but that's it, what you do in probabilistic machine learning, in one form or the other. And in this case, what you do is you fit a Gaussian mixture model. And why do we use a Gaussian mixture model? Because we represent clusters by Gaussian distributions. And using these Gaussian distributions allows us to find out the degree of belonging as the posterior probability that the cluster assignment is corresponds to a particular cluster given the observed data. Yeah. What are your questions regarding soft clustering using Gaussian mixture models? I have tried to make the discussion more clear in the course book, so there will be a new version released by the beginning of next week, I hope. This is kind of the only point, this soft clustering, where I don't know any method that avoids a probabilistic model. And this comes out so naturally here to use probabilistic models because this gives such a clear interpretation to degrees of belonging. What do you mean by degrees of belonging? Well, we mean here in this probabilistic modeling, it's a posterior probability. It's a well-defined concept, a probability. Yes? Yes, so the question was, what's the mechanism to update these parameters given the degrees of belongings? And the basic idea is to do a maximum likelihood estimation. So you choose these parameters to make the probability that you have, that you kind of observe or get these degrees of belonging maximum. And you can work this out, and what you get are rather intuitive update rules. I write it here. So the Gaussian mixture model parameter updates are as follows. The cluster probabilities, so the probability that that the data point is drawn from cluster 1 is just the sum of all the for all data points of the degrees of belonging to cluster 1 divided by all data points you have. Similar for the cluster probability 2, you sum the degrees of belonging for all data points that they belong to cluster 2 and normalize by the number of data points. How do you get an estimate for the cluster mean? Well, you do a sample mean, you average all the data points you have, you normalize it, but you have to take into account that each data point only belongs to a certain degree to cluster 1. So you have to weight this using the degrees of belonging. So here, degree of belonging to cluster 1. And you normalize this not by the overall data sample size or number of data points, but by the effective number of data points in cluster 1, which is the sum of all degrees of belonging to cluster 1 over all data points. So this here is the effective cluster size of cluster 1. And the same game for mean vector 2. You normalize by the effective size of cluster 2, and you take the sample mean or the weighted sample mean using the degrees of belonging to cluster 2. So this here make sure that if a data point belongs to cluster 2 only 50% or 0.5, so this would be 0.5, then this component in the sum for the mean only has weight 0.5. Or if this degree of belonging is 0, you don't take into account this data point at all for the cluster because it doesn't belong at all to this cluster. Yeah, and similar rules you have for the covariance matrix estimates, which I don't repeat here. Or maybe there was one, maybe I will for cluster 1. There was one question, quiz question regarding the invertibility of the cluster covariance matrix estimate. So we use the sample covariance matrix. This is called sample covariance matrix. Times xi minus the cluster mean for cluster 1. And we weight this again. We always weight each sample using the degrees of belonging. And this sum here, so I equal 1 to n, this sum here can have rank at most, the rank of this sum, so the rank of this covariance matrix, is upper bounded by n. Because you sum here n out, they are called outer product, so this is called an outer product. So this is now hardcore linear algebra stuff, but it's good to have it heard at least. So this is an outer product of rank 1, and you sum n of these rank 1 matrices. So you can show using the fundamental laws of linear algebra that the rank of this whole estimate is at most n. And what's the size of this matrix? What's the dimensions of this matrix? How many rows and how many columns has this estimate of the covariance matrix? Sorry? No, so you compute here this feature vectors with its transposed. How large is the feature vector? D. So this is a D times D matrix. And if this D would be larger than the sample size, then this matrix here would have a rank smaller than its size, and this means it's non-invertible. And if it's non-invertible, by the way, this whole modeling breaks down because this Gaussian distribution here is only defined for invertible covariance matrices. So whenever you have the case that you have less data points than the length of your vectors is, this whole thing doesn't work anymore. And you have to come up with something else. One idea is just to don't estimate, directly estimate the covariance matrices, but to set it to a fixed covariance matrix. To say, well, the shape is always similar, it's more or less symmetric. So let's say we fix the covariance matrix of the cluster to an identity matrix times some factor sigma square. So this is a positive number. And we only learn this parameter here. Okay. What other questions do you have? Yes.
The sum of P1 cap and P2 cap is 1, right?
Yes.
So if we know one, we automatically know the other.
Yeah, but this works only in the case where you have two clusters.
Yeah, but even if we have n clusters, the last cluster will be...
Yeah, you have n minus 1 degrees of freedom, or k minus 1. Yeah. Yes?
So what's the benefit of using these probabilistic functions? Why don't measure the distance to cluster means?
So,
Compare them to each other?
so the question was, why using a probabilistic model to come up with a soft clustering scheme? Why not just use the distances to the cluster means, which are unknown, by the way, and then compare them? Yes, but how would you work it out in a precise, in a rigorous way? You can compute the distances, but how do you compare the distances to the cluster means? And how do you update then the cluster means based on these distance measurements? I don't know. So if anybody knows about a soft clustering algorithm or a motivation of this soft clustering algorithm, which does not refer to Gaussian mixture models, I'm happy to hear. Okay. So I suggest to have a break of 10 minutes and then we go into the finale grande of the course, which is about how to automatically learn good features.